Welcome. Today we look at the friction factor for packed beds. Okay. Beds of many different materials are very relevant for biological engineers. We'll see some examples in the next slide. So we're going to look at the friction factor for packed beds. Packed beds are used in many biological processes. For example, water and wastewater processing, the undesirables are removed by microorganisms or other agents in a packed bed of soil, for example, in certain stages of such processes. Okay. A rigorous analysis of flow through packed beds is rather difficult, right? It is flowing through tortuous channels in a bed of, let's say, soil. So a rigorous analysis becomes difficult. Even if an effort arrives at a representative set of mathematical equations from first principles, they may not be easily solvable. Okay, this is normal difficulty. However, packed beds are widely used, and therefore we need some way of having some insight into them, some understanding, so that we can use it for designing those operations and for operation of those. One can use a simpler analysis for such a thing. And whatever we're going to see now, the friction factor approach, gives us one such simpler analysis approach. We are going to replace the tortuous flow path inside the beds through the voids by a set of identical parallel conduits of the same length as that of the bed. Okay, so the actual path could be something like this. So we're going to replace all those by path through a series of parallel cylindrical conduits, or parallel conduits itself. Okay, yeah, usually cylindrical, identical parallel conduits of the same length as that of the bed. Let the radius of each conduit be r. Okay, so it's cylindrical, and the total cross-sectional area of the conduits is number of conduits times the cross-sectional area for each conduit. That we'll take to be S. Okay. We'll use a representative hydraulic radius to make the result somewhat extendable to many cross-sectional geometries. You can consider other cross-sections also. And as long as we use the hydraulic radius, cross-sectional area by wetted perimeter, remember the definition, we can extend this to other geometries also. Let the particles be uniform with point contacts between them. This is an idealized situation for analysis. And we'll assume laminar flow in the conduits to begin with. The total drag force per unit cross-sectional area in the parallel conduits is the viscous drag force plus the inertial drag force per total cross-sectional area. Okay. Something called the viscous drag forces, something called the inertial drag forces. So Fd, the total drag force, is a sum of the viscous drag forces per unit area plus the inertial drag forces per unit area. Now let us focus on each conduit with a radius r. We have assumed laminar flow, and therefore the average velocity in the conduit is given by the laminar flow expression. We average velocity in a laminar flow is minus delta p r squared by 8 mu l. Okay, this we have already seen. Equation 3.4.2-17. We've also seen that minus delta p equals 4L tau w by d, okay, or 2L tau w by r. Okay. V is just added to emphasize the viscous component. Tau w is good enough, the wall shear, but V is added to emphasize the viscous component. And this is normally found in the formulations. This is there in the book, so we'll follow the same thing here. Now substituting this expression for minus delta p into the previous expression, this 3.4.217, we just take the minus delta p here and put it there. We get V average equals 2L tau wv by r, okay, that is 2L t tau wv by r for minus delta p, The remaining are the same, r squared by 8 mu L. Okay. And if we transpose, we get tau WB equals 4 mu V average by R. And we already know that the shear stress is the viscous force divided by the surface area. And to generalize it to channels of any cross section, we are going to express it in terms of the hydraulic radius, cross sectional area by wetted perimeter. And therefore, FV by S is nothing but K mu V average by a certain RH. Okay, so you see R we have here, and we have replaced R by RH, and therefore we have this expression for FV by S. Equation 3.9.3 minus 1, dash 1. For the inertial component, the inertial force per unit cross-sectional area of the conduit is Fi by S, that is tau W, the inertial component, tau Wi. From 3.9.1-7, you go back and check what that is. We get tau Wi is nothing but half rho V average squared times the friction factor. Okay, this is the inertial component. So the viscous component is due to the wall shear, the inertial component is due to the flow itself. So half rho V average squared times F. Let's call this some K2 times rho V average squared. 3.9.3-2. So the total drag force per unit conduit area is nothing but this plus this. Okay, Fd by S is the total drag force per unit conduit area. K1 mu V average by RH plus K2 rho V average square. 3.9.3-3. Now if you focus on the entire bed, which consists of many different conduits and so on, and let us define the volume of voids in the bed by the total bed volume as the porosity epsilon, 3.9.3-4, or the cross-sectional area of the imaginary conduits in the bed. We have replaced the various paths by these straight paths. So cross-sectional area of the imaginary conduits in the bed times the length of the imaginary conduits. So this gives, we are just equating the volumes here. So the total volume of these straight pipes, okay, straight conduits, must equal the volume of voids in the bed. That's essentially what this says. So cross-sectional area of the imaginary conduits in bed times the length of the imaginary conduits, that gives you the volume of the imaginary conduits, that must equal the volume of beds. And CS area of bed times the length of the bed is nothing but area of the bed, length of the bed is nothing but the total bed volume. That must be your epsilon, your void fraction. Sorry, this is the void fraction, porosity, whatever, void fraction. By one of our earlier assumptions, the length of the imaginary conduits is the same as the length of the bed. So this and this can be cancelled. Therefore, the cross-sectional area of the imaginary conduits in the bed divided by the cross-sectional area of the bed is your epsilon. Equation 3.9.3-5. The mass flow rates through the conduits are all additive. Mass is a scalar, the mass flow rates are all additive. Also, the total cross-sectional area of the conduits, we are going to call the total area of the conduits as S. So the S is nothing but the cross-sectional area of each conduit times the number of conduits. Therefore, rho V naught average squared S naught equals rho V average times S. Okay. So mass times the velocity times the area has to be the same, because we are considering two different situations here. Since density is a constant, we can cancel out those. This is nothing but mass conservation, nothing else. Okay, mass rate here must equal the mass rate here. So mass by unit volume and so on and so forth. You can work out the units. It will turn out to be mass rate. Since the density is a constant, V naught average by V average equals S by S naught. That is the same as epsilon. or V average is nothing but V naught average by epsilon. Equation 3.9.3-6. We did the above few steps because V naught average, the superficial velocity before it reaches the bed, the velocity of the fluid before it reaches the bed, or the empty tower velocity, is much easier to measure compared to the velocity in each conduits. Each of these imaginary conduits or conceptual conduits that we have looked at, it's a lot more difficult to measure. They are conceptual anyway. Whereas this can be measured, the cross-sectional area by the wetted perimeter, especially when before it reaches the bed, is very easy to measure. Cross-sectional area by wetted perimeter is your hydraulic radius. Here you are looking at volumetric flow rate divided by the area. That will give you the velocity. Let us relate the pressure drop across the bed to measurable parameters, and let us focus on the particles in the bed. The aim is to express the relevant equations in terms of measurable and calculable particle parameters. That's what we are trying to do here. Okay, remember, we are looking at the bed. We are approaching the bed in some way with our view so that we can get some useful things for design and operation. The total surface of the particles, total surface area of the particles, is nothing but NP, the number of particles, times the surface area of each particle, and that equals AS. Equation 3.9.3-7. NP is number of particles, SP is the surface area of each particle. And we are assuming point contact, so we are neglecting loss of surface area due to contact. Oh, it's said here. Recall, we have assumed point contacts between particles. There is no loss in surface area due to contact. The total surface area of particles will equal the total surface area of the conduits. And if we assume uniform particles, then the number of particles is nothing but the volume of solids in the bed divided by the volume of a particle. So volume of solids in the bed is nothing but S naught L. S naught is the surface area length. This will give you the volume. Volume, you subtract the void volume, which is epsilon times the total volume. From the total volume, you get the volume of solids. So volume of solids in the bed divided by the volume of one particle, Vp. 3.9.3-8. S naught is the cross-sectional section of the empty tower and L is the bed length. And if you substitute 3.9.3-7, which is the surface area of the total particles, in 3.9.3-8 here, we get, instead of we are going to substitute NP here. NP is nothing but AS by SP. AS by SP equals S naught L into 1 minus epsilon by Vp. Therefore, AS is S naught L 1 minus epsilon by Vp times SP. Equation 3.9.3-9. The hydraulic radius is nothing but CS area by wetted perimeter, and if you do the manipulations, you will get epsilon naught S naught L by AS, surface area times length by the AS, the cross-sectional area times the length divided by the surface area, that's wetted perimeter into L, and that would equal epsilon naught S naught, that is S L by AS. 3.9.3-10. And if you substitute AS from the previous expression into this, we get RH, the hydraulic radius, as epsilon S naught L divided by S naught L into 1 minus epsilon. We are substituting for AS here. S naught L into 1 minus epsilon SP Vp. Cancel out the common terms. You are left with epsilon Vp divided by 1 minus epsilon SP. 3.9.3-11. I think this has to be by Vp, right? Yeah, RH. Yeah, this is by Vp. So note there has to be a by term here. Shall I correct it right away? Yeah, might as well. So I put in divided by Vp and fine. By Vp, and therefore the Vp goes up, and you have this as the RH, equation 3.9.3-11, and substituting this into 3.9.3-3, check what that is. We'll get the drag force as this equation. Okay, please stop the video here, go back to 3.9.3-3, substitute RH into that, and see whether you get this expression for FD. Go ahead and do that, please. Stop the video here, pause the video here, go ahead and do that, come back. Okay, now you know how to get FD in terms of this by substituting RH and other variables into the earlier expression 3.9.3-3. We'll call this 3.9.3-12, and we can express the drag force as a product of the pressure drop times the effective area. So FD, let us express as minus delta P times S naught epsilon, and equating the two expressions for the drag force, the inertial and the other component, you get this expression minus delta P S naught epsilon equals S naught rho L times 1 minus epsilon by epsilon squared SP by Vp, K1 mu F naught V naught average 1 minus epsilon SP by rho Vp plus K2 V naught average squared. So just I'm just simplifying this expression, getting in terms of minus delta P by rho L on this side, and I put in a rho here. So this naught S naught will certainly cancel. This rho L I've brought to the other side. So you have 1 minus epsilon by epsilon cubed. That epsilon I brought down here. So epsilon cubed SP by Vp, and this term is the same. 3.9.3-13. For a sphere, SP by Vp is nothing but the surface area divided by the volume, pi dp squared by pi by 6 dp cubed, where dp is the particle diameter, which will turn out to be 6 by dp. And so for any particle, if we define an equivalent diameter, so there is no guarantee that the particles are all spheres. So let us define an equivalent diameter on the same lines as that of the equivalent radius. So equivalent diameter is the diameter of the sphere having the same volume as that of the particle, and a sphericity as the surface area of the equivalent sphere divided by the actual surface area. So this gives us some link between the idealized sphere and the actual particle. So we are extending this to whatever particle, and 3.9.315. So phi s is nothing but pi dp squared by sp, and therefore sp is nothing but pi dp squared by phi s, and delta p by vp will turn out to be pi dp squared by phi s pi by 6 dp cubed. This is written, we are writing vp from the, delta p by vp will turn out to be this, which is 6 by phi s dp. Okay. So this is 3.9.3-16. The values of the sphericity are known for various commonly used particles. Okay. So we take a certain type of sphericity and we can substitute that, and the analysis that we have done for spherical particles, we have kind of extended to other particle shapes also by the use of this sphericity. Now let's recall an earlier equation, which is this. Okay, we have already seen this. This comes from the drag force coming from two components and so on and so forth. 3.9.3-13. From experiments, Ergun, a scientist, he found that K1 turns out to be 150 by 36 over a wide range of experimentation. K2 turns out to be 1.75 by 6. And therefore, for a packed bed, the pressure drop is one of the important design parameters. The pressure drop becomes minus delta P, or pressure drop equation becomes minus delta P by rho V naught average squared times phi s dP by L epsilon cubed by 1 minus epsilon equals 150 by phi s dP 1 minus epsilon rho V naught average squared by mu plus 1.75. Essentially substitute this and then recast this expression, we will get this. Okay. 3.9.3-17. This is called the Ergun equation, which is an important equation for packed beds. Okay. So that we obtained by using the friction factor approach for packed beds. This is highly useful in the design of packed beds. And it works for most packings except packings of extreme shapes such as needles, rings, or saddles. It's not so reliable, or we get an estimate out of this and then we need to use a huge, what should I say, fudge factor or a safety factor and then design. That's what we do. So by comparison with the friction factor defined earlier, we can define a friction factor for a packed bed as F for a packed bed as minus delta P phi s dP epsilon cubed by, so Fs by area divided by this term here, okay, the kinetic energy per unit volume term, rho V naught average squared L by 1 minus epsilon, equation 3.9.3-18. And if you substitute this back into the earlier expression, we get the friction factor for a packed bed as 150 into 1 minus epsilon divided by phi s, the sphericity, times the Reynolds number plus 1.75, 3.9.3-19. And at low Reynolds number, if Reynolds number is low, 1.75 turns out to be negligible compared to this term, and therefore you can just write F PB at low Reynolds numbers as just 151 minus epsilon times phi s times Reynolds number of the particle. Reynolds number of the particle means we are taking the particle diameter for say rho V d by mu. Rho is density of the fluid, V is the velocity of the fluid, diameter is that of the particle, divided by mu, the viscosity of the fluid. 3.9.3-20. Through substitution of the expression for FPB back into the earlier expression, we can get minus delta P phi s dP cubed epsilon by this L V naught average mu into 1 minus epsilon squared is 150. Okay, putting it back there and recasting this, you would get this. Or minus delta P, this is just a mere rearrangement of the equation, minus delta P S naught phi s dP squared epsilon cubed, S naught V naught average L mu 1 minus epsilon squared is 150. This is called the Kozny-Kamenn equation, which is also useful. S naught V naught average is the volumetric flow rate, and if the sphericity, the diameter of the particle, and the void fraction are constants, the flow rate is directly proportional to the pressure drop and inversely proportional to the product of the radius times, the product of the viscosity times the length of the bed. Okay. So this is what it turns out to be. Okay, so S naught V naught average is the flow rate. We have taken it to the other side, and we get this. Flow rate is directly proportional to minus delta P and inversely proportional to L mu. The other things remaining a constant. Phi s, dP, and epsilon remaining a constant. Equation 3.9.3-21. This expression is important. This relationship is important. The flow rate is directly proportional to the pressure drop and inversely proportional to the viscosity times length, is called the Darcy's law, and it has very, very wide applications. Okay. Darcy's law is used in research significantly. Fruits, the application is only limited by imagination. As long as you have something that can be viewed as a packed bed, even fruits, then the motion of the fluid through the fruit and so on and so forth. Then you can apply Darcy's law there. Flow rate is directly proportional to the pressure drop, inversely proportional to mu times L. At large Reynolds numbers, the first term in the right hand side of 3.9.3-19 becomes negligible. What is that? 3.919. At large Reynolds numbers, you have Reynolds number in the denominator, therefore this term becomes negligible compared to 1.75, and therefore the friction factor of the packed bed at large Reynolds number equals 1.75, which is called the Blake-Plummer equation. Just expanded, you get equal to 1.75. 3.9.3-22. And the above equations can be used to predict pressure drop across beds. Pressure drop is a very important design parameter. And we have seen a way by which we can get a measure of the pressure drop by using the various measurable parameters. The pumping requirements across packed beds can be estimated once you know the pressure drop. And so we have seen the application of the friction factor approach to various different situations, to a piping network consisting of straight pipes and pipe fittings, to a contraction, a stenosis in a biological situation, for motion, relative motion of a solid and a liquid through a liquid, relative motion between a solid and a liquid, and now packed beds. Packed beds are very widely used. Okay, we'll stop here for this class. When we come back, we will review the momentum flux chapter, large chapter, momentum flux chapter, and then we will move forward. See you then. Bye.